It wasn't my idea to recap all of the electrolytic capacitors in this frequency generator. These two 800 microfarads appear to be fine, looking at them with this. One of these was bad. It's a plus and minus. They're shown here as the 20 microfarad 50 volts. They're actually across a 22 volt supply, plus and minus. I have some 22 microfarad I believe. Yeah, 22 at 50. So I'll replace these two just for the hell of it. They were located here and here. So we'll turn it on, and you can see in the oscilloscope with the the 1 volt output is live and well. We're still not getting an output from the other side. So we'll have to see where it goes or why it disappears, which means doing some troubleshooting and following the chain of events when the signal leaves this area and moves ahead. Then we have I guess it's an oscillator and amplifier, whose output then goes down to the frequency selection stuff and appears here on the voltage output pot. And then it goes into the output amplifier. So look on the well, let me put the probe on one side of this pot, which is right here. Better turn it on. Better turn it on. And you see in the oscilloscope, I'm going to touch it again. There we go. The pot itself, this output is what goes to the amplifier. And you can see in the oscilloscope the signal's there. I'm going to turn the knob for you to see the shaft rotate here. And the pot's dirty, but the knob goes down. But the voltage at the tap, which is the voltage here, which goes down here and into this amplifier. So we're getting signal that far. And again we have, I'll get a close-up view here, two thermally connected transistors. Only they're a much bigger thermal connection. That is, they're not as intimate as, say, these two. What you can see is designed to handle or dissipate much more heat. So we're getting a signal to these transistors that are these two right here. Well, I've looked through these amplifier transistors and I've worked my way to this piece of coax right here. And it's the output of the amplifier. Schematically, it's this piece of coax right here, where the signal comes out and enters these push-button switches on the front of the panel. And I'm going to look right here, which is turned on again, which is this. And you see, I have a good signal there. In fact, if I turn it up, how high does it go? So this is 10 volts per division. Volts. So peak to peak we have 20 volts there, a little bit more. There's that 10 megahertz. Here is that 10 hertz. The pot, you see, has some noise on it. That's the voltage adjusting potentiometer. And it does indeed vary the output. Down to 0. Which it should, it's controlling the amplifier. So the problem lies in the attenuator. The attenuator board lays here. It's held in place on these standoffs by 2 screws with an aluminum shield over it. This is the coax, and I do have a signal here. So there's merely a series of switches that go down. I've cut off the bottom, but they go out here. So, and I verified I don't have a signal at the B and C connector. So I'm going to take this board loose, take the aluminum plate off, and squirt all of these switches with contact cleaner. I can't get to this underside of the board because there's a big piece of aluminum here on the case. So once I get the board out, or twisted so I can read it, I'll go through the switches one at a time with an ohm meter. We're going to spend some time on the oscilloscope now. This attenuator board was probably designed before this. It was designed to be mounted on 2 standoffs. But the second standoff is missing, but it's not gone from this model. There's no, if I were to put a screw in, it wouldn't hit anything. It was just tightened into a hole in the board. I don't very often say designers should be shot, but this threaded hole here is a match to this one. So the original design had this board supported. You see, this metal doesn't go back far enough. So in turn, the designer put a number 4 screw on the front panel. The screw's loose. Its head is captive under the decorative front panel. So I was able to get that screw off, that nut off fairly easily. But turning it over, that screw there is almost impossible to get to. Remember, you can't get to the head of the screw because it's covered by the front panel. It's a blind, but it's not fastened in place. It wobbles around. See the screw wobble? Anyway, that's my tirade for the night. This thing is pretty well built, I will say that. Capacitor is wide open, which tells me it's at the high end of a frequency range. So if we look at the oscilloscope, what's supposed to be a 1 volt output is down here. And a 10 volt output here in yellow. And you note it is 10.3 volts. I'm going to, and it's at 10 megahertz, 10.21 right now. I'm going to close the capacitor, which lowers the frequency. Go in here and change my horizontal time base. And I'm down to 10 on the dial, which is 999 megahertz and 0.98 volts on the labeled output. Now the 1 volt, let's look at the 1 volt output. Right now it's sitting there about 0.9 volts. Watch what happens as I crank the knob back up to 10 megahertz. Don't worry about the... Okay, this height is almost constant. See what happens to this 1 volt signal? Certainly dies off. And back to... that's 1 megahertz. Now, let me go down to times 10. And right now I'm at 10K times 10. A dial setting of 10. We should be 100 kilohertz. It's a little bit off at 96 kilohertz. And there's 1 megahertz. Now watch the voltage as I go from 10 megahertz down to 1 megahertz. You see there, it's perfect. They're still just the way they were when we started. The next band down, just a horizontal time base, and that is 10 kilohertz. That is 100 kilohertz. And watch as we go up, the amplitudes stay nice, very nice. And I'm at 110 kilohertz. Should be 1,000. It is 1,000 kilohertz. We'll take it up to 10,000. 10,000 or 10 kilohertz. We go another step down. We're at 1 kilohertz. That's 100 hertz. And the last multiplier that's 10 hertz. And we'll run this up to 100 hertz. A little bit of funkiness there. Let's that's not 60 cycle bouncing around. It's some time constant in the amplifier. Maybe in the level control circuit. We have that. Oh, much, much worse. And it goes away. So I think that's a time constant in the level control circuit. We'll go from the 1 multiplier, which we are now, to the 10 multiplier. And no variation, none of that Ripley stuff. The dial on front is set at 10 volts. And the attenuator is set at 10. And we're getting 10. If I turn the knob down, it goes to 0 volts. So the whole span, voltage-wise, is in that knob. Once the knob is set to a voltage you're happy with, for example, there's 10 volts. If I hit the attenuator to go to 3.16, I go to 3.17. If I hit the attenuator to output 1 volt, I have to turn this up a little bit. You'll see it's 1 volt perfectly. So the push button attenuator is only calibrated when the knob is calibrated. I'll turn this up on end and we'll talk about that some more. I've got it turned off so I can upend it. So this knob and frequency, all these push buttons seem to work. This attenuator is only accurate if we adjust this to, say, 10 volts. Then it becomes accurate. So this truly is 0 to 10 volts. And the output is in RMS, so that's good. So what's nice about, or what could be nice, is if you wanted to put a frequency counter on this, you just hook it up here. It does not affect this output at all. So you could use this output for sweep synchronizing or for a frequency counter. This is not sold as being a low distortion audio oscillator, although the specs are claimed pretty good for it. But it's certainly not a Hewlett-Packard 200 series. One more thing, we'll look at the back. This is the non-standard fan outlet. There is an input here called sync in. Now that gives me, I can do two things with that. I can apparently sync this oscillator to an outside source if the oscillator is pretty close to the desired frequency. I believe I can also input a DC voltage here and get some amount of FM out of this. So I'm not going to calibrate it or worry about that frequency-wise. The attenuator is not calibratable. There is a level output that I could adjust it to. So when this dial says 10, this dial says 10, I can get 10 if I adjust that. I think that's all. So this was a $70 signal generator. I believe it to be made in 85, maybe 84. There were 83 date codes. I think one of them was in 84. All right, well, if you've stuck around this far, thank you.